So issues on the unsupervised learning. So here, yeah, the question comes from this BIT file. Actually, this is where the problem is coming from. This is the where it is. So BIT means BIT membership of XT to cluster I, to cluster CI. Okay. So in other words, BIT means whether item T, item XT belongs to cluster CI or not. We already did clustering, so you know that data might belong to only one cluster. It doesn't belong to any of the clusters. Okay. So this B matrix I mentioned is something like this. So it shows the membership. Okay, C1, C2, C3. As an example, we may have X1, X2, X3, X4. We have 4 clusters. Each data belongs to will belong to one cluster, right? If it belongs to one cluster, I'm going to put 1. If it doesn't belong to other cluster, I'm going to put 0. As an example, okay, this is just a random example. Let's say X1 belongs to C3, I put 1. X2 belongs to C1, I put 1. X3 belongs to C2, X4 belongs to C2. I put 1 for the two. This shows that X4 belongs to cluster C2. And I'm going to put zeros for others. Okay, so that's what I meant in that video. And then if you look at here, you only need to update the cluster that item belongs to. So for example, X4 only impacts cluster C2, it doesn't impact other clusters. That's what it means. So only work on the cluster it belongs to. It's only going to update the mean of cluster. That's what it means. Okay. It's not going to impact anything on the other clusters. For example, X will only impact cluster I in this case. Okay, it doesn't impact this cluster, it doesn't impact this cluster. Okay, it's not going to have an impact because the membership is 0. It's not going to have any impact. And this is the formula. So how much the clusters will be moved. If it is 0, it's not going to impact this center of other clusters at all. It is 0. If it is 1, it's going to have some update on the clusters. Okay. So makes sense now? A little bit? Yes. It's just formalization. Okay. Probably this is the way we do it, but when you put into a formula, that's the way it works. Okay. Mouse doesn't work. So this is a very important topic. This is the core of machine learning. This is not covered directly in the main textbook. This topic is covered in this other book I provide in the syllabus, Learning from Data. Okay, what is learning? We have historical data. For data samples, we know their attribute values, X, and we have a decision that has been made for the historical data. For credit approval, it is provide credit or decline credit, for example. Or if it is a family car, in a car example, is a family car, yes, no. Whether this person is likely to buy this item if we market to that person. So that is yes or no, and that's a decision again. So we have the decisions made based on the historical data. We showed this commercial and the person bought the item, okay? Or we showed the commercial, the person did not buy the item, okay? So we have those decisions like why? We have seen them. By looking at the historical data, okay, what we try to do is, actually there is an ideal function based on this, based on the real scenario, we have an ideal function which we don't know. For example, and there are times that we cannot know either. For example, to give a credit or not. If a person is likely default, basically, we should not give a credit. If a person is likely to make payments, then we should give the credit. So how can you know whether the person will make the payments or miss the payments in the future? Okay, there are too many factors that we cannot control. We just look at the existing time. But let's say there is an excellent ideal function that tells you this person should be given credit and this person should not be given credit, and it always makes the correct decision, okay, based on the current X values. So that is the ideal function, but we don't have it. So what we do is we assume that there is a hypothesis set. Okay, from this hypothesis set, we search the best hypothesis, best function by looking at training examples, and hopefully that best function, hypothesis G, in this case, is similar to F. So we are trying to find the best hypothesis similar to F. So that's our problem. Okay, that's what we are doing. That's a machine learning problem. So this is the learning algorithm. Learning algorithm explores the hypothesis space. Okay, that's the goal of the learning algorithm. I can move on this one. So let's see an example. Okay, this is a very simple hypothesis set. Okay, what we do is in my hypothesis set, I multiply each attribute value with a weight. Okay, for a person, I multiply each weight as an example with a weight, each attribute value. For example, age, education level, salary, being marital status, okay? So annual income. So all those things, okay? For each attribute, I multiply with a weight. And if that weight is greater than a threshold, I say that, okay, I say yes, otherwise I say no, okay? So this is a hypothetical case. So what is my hypothesis set is WI, the weights. I don't know the best set of weights. I don't know whether age is better or salary is better to give a credit or toward it. I don't know that. Okay? It's something to learn. And that final decision will be based on that threshold. So this is my hypothesis set as an example. All possible combinations of W's, the weights, will make my hypothesis set along with the different threshold values. Okay? So that's what I do. And then I credit in this case. This formula, can be simplified into a single formula. So what I am going to do is just to explain. So there's a threshold here. Okay, usually it's a greater or less than. I can move threshold on the other side. I can subtract threshold from the summation on the left. Okay, if that's my threshold, then I'm going to look at the sign of that difference. If the sign is positive, it's approved credit. If the sign is negative, then deny credit. So I can convert the formula in this way. Okay? So that's what I did here. I check the sign. Okay, so I subtract threshold and then look at the sign. Sign will tell me approved one. So I combine two formulas into a single one. So this is the way it goes normally. But usually, this is a complex formula. What I'm going to do is the dimensions or attributes start from 1 to D. So I have D dimensions. I'm going to label this, replace threshold with W0. Okay. that's a new name, new variable. I'm just going to put this W0. It's not directly related to any of the attributes I have. And I'm going to multiply it with x0. X0, this our attribute start with from 1. And I will set x0 as 1. Okay. So I'm going to have just W0, etc. Then I can start my summation from 0 to d, and I can make this as put this expression into this form. So this is the way it's going to look like initially. So this is a perceptron called perceptron. So I would like to find the line that separates the data. Okay, that's my hypothesis set. Hypothesis set is all possible lines. Okay, and my solution will be is the best line that separates them. So any line is part of my hypothesis set. So my goal is, in what I explore, is to find the best line that separates from a circle from a triangle. Okay, that's the machine learning. What we are trying to do. So this is this formula in vector notation, or this perceptron example is this. So my hypothesis set is all possible lines. My algorithm will find the best line that separates the two classes. Okay. In this case, the example I provided, my hypothesis set was all rectangles, and I need to find the best rectangle that separates positive and negative. That's the case. Now this part is, I recommend you like to take notes, but my suggestion is just listen to this part. You can watch the video later and then take notes if needed, because this one is a little bit complicated in my opinion. So let's say this is the general starting point. So we have original bag. The original bag, I have red balls and green balls. Okay, this is the complete data set. And I have a sample from this data set composed of red and blue. So I pick, let's say I have hundreds of balls. I randomly pick 10 of them and make it my sample. So let's say in the original bag, I have the probability of red balls. Let's say 30% of the data is red. So if I pick just 10 of them and I look at my sample, probably the ratio of red balls may not be 30%, right? It may not be 0.3, okay? So that's my rho, okay, just to say. So rho is my observation, mu is my real fraction of red balls. So I try to make my judgment based on what I have. I don't see the complete fact. It's a black bag. I don't know. I am not counting them. I just pick 10 of them and I try to make a decision. Okay. So what I want is ideally, this rho to be close to mu. That's ideal. So if I pick 10 and look at my rho, okay, rho is the fraction of red balls. If it is the same as mu, the real fraction, then that's a good representation of the sample with respect to the original data set. Okay, that's what I am trying to do. Okay, but the question is, I don't know mu. It's not given. If you know mu, you can solve the problem. Okay. What we would like to do now is, okay, so that's where we are. I don't know mu, but what I'm thinking is, can I limit the error? My error is, in this case, the difference between rho and mu. So if I can limit the error, then that's a good approximation. Meaning, I have rho, my fraction of red balls, and mu probability of red balls in the real environment. If the difference is the error, I may try to limit that error. So what I can put here, this expression is important. So if you look at this, rho minus mu is my error. Let's say the real is 0.4. This is It's hypothetically, okay? And this is rho is 0.3. I know that the error is now 0.1. I am close enough, but it's not accurate, okay? But what I can do is, I cannot make it 0, but I can limit the error probabilistically, okay? I may say that the error will be at most 0.1 with a probability of 0.9. Or let's say with a probability of 0.8, the error will be at most 0.1. I can limit that. So that is something that we can achieve. Does it make sense? I cannot, because there is always a scenario that your algorithm may fail, but probabilistically, I may guarantee that the error could be at most 0.1 with a probability of 0.8. Okay? I can limit. So how can we, make better probability, improve probability? If you use larger sample, if you get, rather than getting 10 volts, get 50 volts out of 100, then you are going to have a better probability. You are going to reduce the error. Or what you should do is you should decrease this error. Okay, you should have a little bit higher error. You should accept a little bit higher error. That's the other way you can, play with the system. So there is something called Hofding's inequality. Okay, this is a very interesting. This is a proven formula. So you don't need to prove it. I don't need to prove it. So I am on the same page with you. So we are lucky someone has done it. Basically, what this says is the probability epsilon. Okay, this probability, if you look at this one, is always less than or equal to this expression 2 times e to power -2 epsilon squared n. Okay, that probability is limited by this one. But this is very interesting observation. Okay, this is you don't need to understand how this is derived, but you should know the red parts that I highlight over there. Firstly, look at what I have from the left side on the right side. Which variables do I carry from the left side to the right side? Which variables that you see? Error. Just the error. Okay. So this is a very good, important problem. The error, or this expression, this probability, does not depend on what rho or mu is. It only depends on the error that you specify. So without knowing mu, because you don't know what mu is, because I don't have the access, I don't have access to the real bag, I can, limit my probability. I can determine my probability. Okay. So let's look at this. Let's write this in an open way. So if you write this, it is 2 times, so there's a -2, e to the epsilon squared times n. Okay, that's the way we do it. So you know that epsilon typically will be a number between 0 and 1. Okay, n could be a number greater than 1. Okay, greater than or equal to 1. If you increase n, then that number will go down. Okay, that number, this expression will go down. So it means that you are going to, the probability of having that error will be lower. The probability of having high error will be lower if you increase n. That's what it says. Or what you could do is you could use lower error threshold. Don't try to make your system perfect. Don't make 0.0001 error. You can maybe make 0.1 error. Okay. So you can use a different threshold for the environment. This is what it says. So first, I'm summarizing this one. I can determine I can limit or I can estimate the probability of error, or I can limit the error probabilistically based on n. and with respect to n. I can limit the probability. That's what this says. This is told as you don't need to know mu because it doesn't appear on the right side. And you can do regular, you just need to know the epsilon and n. That's what it is. Now I am making the transition now. This is part, I think, is the hardest slide. Okay. Because that's the conceptual coverage. So if we may not understand this one, it may be a little bit confusing. So in the assignment, have you started the second assignment? Okay. The second assignment, you are doing a classification about the sentence, right? So let's say that the red and green balls are the correctness of my classifications. So green ball says that my classification is correct. Red means my classification is incorrect for those items. The ones that are green are classified correctly by your K9 classifier, and the ones that are red, they are classified incorrect. Okay. Does it make sense? So instead of balls, now I have this classification. Okay. So if I look at this now, here, green balls means you have a classification result. Classification result is the same as the ground truth, the original label is provided to you. Red ball means your classification result is different. Okay, that's what it means. Okay. So what we have is, I have row. Now this is the important transition. So row means you look at your training data set, basically. You look at your training data set, you get some accuracy. Your accuracy is row. Okay. And this mu, you can assume that is your accuracy on the test data set. One of them is your accuracy on the training set. The other one is on the accuracy, as an example, on the test data. Okay. So I use in sample, out of sample. In sample means training data, out of sample means test data, the data that you have not seen before. So I look at my data, I look at my training data, because normally this is the way we do it. When you build your model, like K9 model or any other supervised model, we never look into test data. We never look into test data until, for example, you work on your training data hours and hours and hours, and you think that your model is not good enough. You think it's going to work in real environment, and you just have one shot, try on the test data. Look at the test data this way. It's just for trial once. So it's a competition, okay? You are going through a competition. You build your data on training set, and the organizer of the competition has the test data that you have not seen. They are going to tell you that they are going to run your program once on the test data. You win it or lose it compared to other competitors, okay? So the test data, that's the logic here. So what we do is now, so I have my accuracy on the training data. I have my accuracy on the test data that I don't know. But what I am trying to achieve is, I want to make sure that my model behaves similarly for my training set and test set. So ideally, if my algorithm works 80% accurate on the training set, I expect that it should work 80% accurate on the test set. Okay, that's my expectation. So this is the way that we build ours. So for each data X, when we apply it, okay, and it's going to, now I change the error, so my training error, and the or accuracy in the other way, because you can look at it as the error, this classification, or error or accuracy. You can look at it that way. If my accuracy is 0.8, my error rate is 0.2. right? So you can look at it. If my accuracy is 0.8, my error rate is 0.2, 1 minus. So I can limit the error probabilistically by using that formula. So this is very interesting, very powerful. But but this is the critical part. Often inequality is just worth one sample hypothesis. One sample hypothesis that you choose. If you pick multiple hypotheses, this Hopkins inequality does not hold. If it is only for one hypothesis, it's going to work. So I'm going to explain what this means. Okay. All right. So what we mean is, so we have the same problem. Okay. I pick randomly one hypothesis. Okay. One classifier. So if I run your algorithms, okay, probably I'm going to get different accuracies. So for example, H1 is the submission of one student, H2 is the submission of another student, H and M is the submission of another student. Each of them could be different, okay? Although you are using KNN, okay, because of the way you use a distance measure, because of the way you use different K values. You may use 3 neighbors, you may use 5, you may use 7. So you may come up with different hypotheses. So each of them is a hypothesis. Okay. Our goal is to find the best one. So this is what we what we are actually working on. So we have multiple hypotheses. How do we guarantee limit the error if we are working on multiple hypotheses? The only way is to make sure that our idea works. For each hypothesis, the one that we pick, we need to make sure that its error is greater than epsilon, or for the second hypothesis greater than epsilon, for the third, fourth, fifth, and hypothesis is greater than epsilon. So if you add them up, this is what you get. Okay. So eventually, what happens is, if you have multiple hypotheses, then you have 2 times m. So m is a coming factor. Okay. Normally, we want to keep the probability very low. Because what is the probability? The probability of having error greater than epsilon. We want to keep this probability very low. But whenever you have multiple hypotheses, this number will increase. Okay. N decreases. You know that if you increase n, this is going to go down, but m will increase this expression. So m does not work in our favor in this case. So what this says is, I'm going to put in a different context, okay? Now different. So this says that if you have billion hypotheses, okay, it's possible that randomly you may pick up a good hypothesis that works very well for the training set, but it may be totally off with respect to test set. That's what this means, what we are trying to solve. So you can increase the number of hypotheses. It's going to fit very well for the training, but it may not work at all for test data. It is possible. So we are trying to solve that problem. So this is where we are. So probabilistically, to limit the error with respect to epsilon, to keep the error greater than epsilon probability, it should be, the probability is limited by this factor. So let's put some numbers here, okay? But I want something like this. I just say P, I'm just going to put error greater than 0.1, okay? So I have a high error. I don't want high error, but let's say my error is greater than this one, is 2 times, okay, m minus 2 epsilon 0.5 1 square, n is I pick 1000. So I can compute this in this way. The probability of error having greater than 0.1 is this one. So I want this probability to be a small number. I don't want the error to exceed this 0.1 error. I want to keep it as small as possible. That's my logic. So now I'm going to look at this problem. Right? This is my hypothesis set. The example we have seen about the family car. Whether a car is a family car or not. You look at the price, you look at the engine. So it's a rectangular hypothesis set, right? Rectangular. So I have prices P1, P2, P1 prime, P2 prime, we have P1, P2, etc. So we are looking at some ranges, right? How many hypotheses do you see in this case? Possible hypotheses? Let me ask a question a little bit different. That the answer is related to how many possible combinations of P1, P2, E1, and E2 are possible. How many combinations? P1 and P2 is a real number. It could be any number. P1, E2 is a real number, so it could be any number. Hmm? The answer is infinity. Because P1 could take infinite number of values, P2 could take infinite number of values, E1 can take infinite number of values, E2 could take infinite number of values. So there are infinite number of rectangles you can draw here. Okay, that's your hypothesis set. So there's infinite number of hypotheses. So the problem is, now I'm going to come back here. If M is infinite, then you cannot limit the probability. You cannot limit this probability. You cannot limit it if you have M infinite. So how are we going to solve this problem? So the answer is related to, it's an observation. Although you see two rectangles here, there's the blue rectangle and yellow rectangle, the green area's intersection. So these hypotheses that you see, they are actually not independent of each other. They are overlapping hypotheses. Okay, maybe this overlap could help us. Okay, maybe it looks like infinite, but we don't need to have infinite because if you look at these two rectangles, they are significant overlap. Okay, so we are going to be so M may not be infinite. It looks like infinite based on the hypothesis set, but it may not be infinite. Now, this is the summary of the learning problem. And this is what I explained so far. So the learning problem has two components. One of them is I would like to reduce the error between the training accuracy and testing accuracy. You can look at that way. I want to reduce that error because I can reduce that error by using this formula, right? Or by using this formula at the bottom. I can do that, okay? So I would like to make sure that the error is limited, okay? That's the first part. The error is limited. Second part is I need to make sure that my hypothesis on test data, the error is very low. That's right. But I cannot control test data. I don't have to control that. How can I ensure that? The only way is I could make sure that my training error is 0. Okay, that's my goal. So if we summarize, so there are two parts of your learning part. You need to guarantee that your training accuracy is similar to testing accuracy. You need to guarantee that it's very similar. And you need to guarantee that your training error is close to 0. So why do we need this? Okay, I'm able to control my model on the training set. You are going to work in your assignment K9. So you can look at, okay, how can you make it better and better and better and better and better? You need to minimize the error to 0. And you also need to make sure that the error that you get for training is similar to the error that you get for testing. And we can do this without seeing the test data. Okay. Because of the how things inequality, I could achieve that. So if you just use the first one, if you just use the first if you just say the error for in sample should be the same as error for out of sample, or error for training should be the same as error for test, then you make it very high error. Like your error is 0.8. So it is too high for an error. So what is the purpose of, yes, it is the same as your algorithm works badly for training and badly for testing. What is the purpose? Yes, they achieved similarly on the training set and test set. So you solve them. But the second part, you need to add the second part is to reduce the error for training. And when it becomes similar to the out of sample error, then you can build this learning problem. You can solve this learning problem. So I'm going to open the floor for questions.
Does this algorithm works for any kind of problem, or it's just of binary problems like yes and no?
It can work for any type of problem.
It's looking to me as if this is working for binary.
Yeah, I mean, to understand the conceptually, I provide. But if you look at this, let me come back here. What is a green ball? Green ball is correct classification. You may have multiple classes, and correct classification means it's exact classification. So it doesn't limit you on the number of classes. It just tells you whether the output is correct or not. That's what binary here is. Is your classification correct or false? You may have 10 classes. Still, you may have an answer whether your classification is correct. Okay, so I am summarizing briefly. I am trying to, we learned that it is possible to limit the error probabilistically, right? That's what I showed you. It's probabilistically, it's possible to probabilistically limit the error. That's a very good thing without seeing the test data. By just using your training data, it's possible to limit the error. That's a good thing. And there is a formula for it, and you can reduce the or you can have a better probability by increasing number of samples you select, or you can have a better probability by lowering the error threshold. So you could work on this. Okay. So we have this option included, but it's not go along with the number of hypotheses. We multiply with the m. Okay, m is certain. But what we said is m might seem infinite, m might be infinite, but the hypotheses are overlapping. So we are going to solve that problem. So people have already worked on it, and there is a concept for solution. So this is the solution slide. Okay, the general for it. We need to count the number of effective hypotheses. Okay, for a selected endpoint. Meaning, what this means is how many non-overlapping hypotheses? Non-overlapping. Let's call it as a growth function. Okay, let's call it a growth function. I'm going to explain growth function a little bit better. Let's call it growth function as MH. If you know the number of effective number of hypotheses, I'm going to put a simple non-overlapping hypothesis. You know that it's MHN. Then we could replace the formula, the error formula that we had in this way. E out, you remember that E out minus E in is my error, right? That's what my error is. Okay, you can take this one on the left side. Is limited by this term. Okay. So if we look at this, there's 2 times MHN. I don't know what it is right now. And then my probability is 1 minus delta. Okay, so delta is only. Okay. And I could have this expression. This could be limited with a probability of 1 minus delta. I don't know what MHN is. But what I observe from here, if MHN is polynomial, it is polynomial. Okay. What is polynomial? It's polynomial.
N with some function.
What is it?
N power by some.
Yeah, the power of n, summation of power of n. So for example, I just make it up, a n to the power 5, b n to the power 4, plus c n to the power 3, plus d n to the square, plus e to the n plus f. This is a sample polynomial. Okay. So I can limit this polynomial, okay, although these are lower factors, right? I can replace this, so this is going to be summation will be something will be less than or equal to x times 6. I can limit it. We agreed, right? I can limit and find the higher polynomial that is always going to be, right? I can do it. N to the power 6. Can I do that? The highest power is 5. I can find an n, or the power of n that is greater than n. If I put here x times n over 6, this is ln. So if you do ln, what happens? Now when you solve this one, 6 will go in front of ln, right? So you are going to have 6 over 2n, and write it on top of it. Then you are going to have a constant here, and the next divided by 10, right? So this is going to be constant, 6 over 2n. So as n goes to infinity, that's going to go to 0. So what we need to do is, I am summarizing this part, we need to make sure that this growth function MHN is polynomial. We just need to make sure that this growth function is polynomial, or the number of overlapping hypotheses is polynomial. If you can show that, you solve it. How are we going to do that? We are going to talk about breakpoint and Wapnick-Cherry-Von Henke's dimension. Okay. That's what the trick is. Are you having fun?
So.
But this is a very interesting. This is the core, the underlying fundamental. Because this is, let me ask this question to you. You are training. You have training data, and then you build a model based on training model, training data. You build a model, and you are going to deploy it in real life. How do you know it's going to work or not? There must be some theory behind it, right? It's not guaranteed to work all the time. How do you know it's going to work? How do you know that the error will be limited when you deploy in a real life? So we need this underlying factor. And this is the second part, okay? This is second part. You need to be really careful. So I am going to, this is a different way of approaching the problem. It's very interesting approach. To find the number of hypotheses, I am going to, what I'm going to do is, I am going to first define my data points. I define my data points. What are my data points? X1, X2, Xn. I pick it from my sample space, okay? I picked it, some points from the sample space. Assume that we have two classes, -1 and +1, -1, +1. And I am going to think about all possible hypotheses for this data set. All possible hypotheses. And I'm going to call it as dichotomy. Okay? And I'm going to look into how many different hypotheses can be developed based on class of each xi. And I'm going to determine the number of growth functions. It's an example now, but that was the theory. Hopefully, the example will make it clear. For example, I am going to pick up n data, and the data that I have is on a linear line. Okay, it's on a line. It's linear. But it's on x-axis. All data points are on the x-axis. I'm going to pick n points. Okay, I'm going to pick n points. The question is, I'm going to determine the number of effective hypotheses. I want to determine the hypothesis. So what I do is, my hypothesis set is based on this function. If x is greater than a, it is positive. If x is greater than a, it is negative. That's my hypothesis set. I don't know what a is. Okay, a is actually the factor I am searching for. It's going to be designed like this. Okay, all data will be on the axis. I pick, let's say, as an example, I pick 3 points. 1, 2, 3. That's the way. So how many possible hypotheses that I have here? How many different hypotheses can I generate based on these 3 points? So what I mean is, how many different outputs can I get? So if you look at this, again, the problem is, I want to make this a little bit meaningful. A is actually a real number. It will take infinite number of values. So it's again going to be infinite. But having infinite will not generate different classifications for me. So what I mean is, let's look at here. If I choose A here, that's my A. What are the 3 x's? What will be the classification of those 3 points over there? Positive. Positive, positive, right? Do you all agree? If I choose A over there, then positive. If I choose A here, not here, what will it be? Positive. Or if I choose somewhere here, they are all generating the same hypothesis now. So this is the same actually. When will it change? My hypothesis output will change. If I pick, let me draw this again. If I choose A here, now my hypothesis, the output will change, right? The hypothesis will be, this data will be classified as negative, this will be positive, this will be positive. Everything on the right side of A is positive, everything on the left side of A is negative. Everything on the right side is positive, everything on the left side is negative. You see that? Right? Or it will change also. Another place, I can pick as many A's in between, the output will be the same, right? It's not going to change. If I pick A somewhere here, it's not going to change. Another place I can do is, I can pick A here. It's going to be negative, negative, it's going to be positive, but that's another way. So I can pick any A in between, the result will be the same. And the last one will be X, X, X. I can pick A anyway, any place on the right hand side, and all of them will be negative. So in this case, I have 4 hypotheses. 4 different. So my growth function is 4. have 4 different hypotheses I can generate based on these 3 numbers. So actually, my number of hypotheses I could generate is limited, or number of functions I can generate is limited based on this hypothesis set. These are all possible. It is all positive. First one is negative, positive, positive. Second one and first one, second one is negative. The third one is positive, or all negative. So these are all, possible hypotheses I can generate based on this data set. Okay? So here I have 4. If I have n data, what will be the number of hypotheses I can get? For 3 plus 4, it's going to be n plus 1. Because you can pick between the numbers, okay, each number, here, 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 any place in the numbers. It's going to be n minus 2, one on the left side, one on the outside. You are going to plus 2, you are going to get n plus 1 possible hypothesis. So this is my growth function. For this hypothesis set, my growth function is n plus 1. Is it polynomial? Yes, it's polynomial. N is the power 1. It's polynomial. So, as a summary, you pick the points first. You don't do the labeling. You don't do the labeling. You just pick the points. You may pick any points you like. Pick the best points that works for you. Get the selected best set of points that will work for you. Okay. Then look at your hypothesis set. Look at whether you are able to, how many different hypotheses you could generate. That will be your growth function. So how many different hypotheses means how many different combinations of labeling of the data using your hypothesis set. In this case, I can only have 4 for 3 data points. I can get 4. If you make it n, it's going to be n plus 1. And for such a data set, you may use it. I can limit the error. It's polynomial because that's where I'm coming from.
So,
yeah.
What do you call it? Why we have to calculate the number of hypotheses?
That's a very good question. So we come from here, okay? Well, let's look at it. So if you look at this, we have this error is limited when limited based on n times to the power 2 times e to the power negative 2, right? You see that right here. And after analyzing the non-overlapping hypothesis, we may convert this expression into this one. Okay? Into this one. So into this is already studied, right? I don't need to prove it. You see that the growth function or number of effective hypotheses is here in the formula. So I am trying to determine the error. So if I know the number of hypotheses, I can determine the error. That's why I'm trying to do. Without knowing this, I don't know it. If you just look at the general, the values of the range of values, you have infinite number of hypotheses, but they are overlapping. How do you know the non-overlapping hypothesis? You need to find that growth function number of hypotheses. And then plug it here. And then you are going to be able to limit the error. That's a very good question. The closest way to understand is the error that you get on training set. E out is the error that you get on the test set. So you don't know. So you analyze or you develop your model based on the data you have, right? For example, you are building Tesla, okay? And you want to make sure that you have a pedestrian crash avoidance problem. So you drive the car with the driver in the streets and you mark the pedestrian, you know that when the car should stop, not to hit the pedestrian. You build that training set. Now you are going to have the car with autopilot in an unseen before, in a test environment. Okay, you are not seeing that now. So E in is the training data, the accuracy that you get on the training data. E out is the actual real life performance. So the error, the difference between them, you should keep them minimized. So your algorithm should work similarly on your training set as a test data. That's what we are doing. So that's what we are trying to minimize. And what you do in addition is you try to minimize the error for training data. So you make sure that training error and test error are similar and training error is close to zero. That's what you try to achieve.
What's M?
M is number of hypotheses. Okay, that's a very good question. I like your questions. So for normally for limit and error for a single hypothesis, if you pick one hypothesis, the error could be limited with this formula. You could limit the error. You can make sure that your algorithm behaves similarly, probabilistically with this value. But if you have hypothesis set, if you have too many hypotheses, randomly you may pick a model that works for training set but works terribly for test set. So to avoid that, okay, that's the problem. So your hypothesis set, if you use the infinite number of hypothesis set, then the formula becomes like M over there. You cannot limit the error. M is number of hypotheses in your hypothesis set. You cannot limit the error. So what we should do is, what we learn is, these hypotheses are overlapping, luckily. So maybe they are not infinite basically. Okay. We have what we need to do is, rather than counting infinite hypotheses, we should look at the effective number of hypotheses. The hypotheses that are really different from each other. That's what we are counting in this case.
I guess I still haven't understand the infinite hypothesis.
So those that overlaps, we'll discard those and just those are different. M will be those.
Why do we have to bring M into the equation?
What is it?
Why do we have to bring M into the equation where we're sampling on one set? Or maybe we have a lot of dimension.
So this is like if you use multiple hypotheses, okay, this is the reason. So your hypothesis is too large, okay. I want to show an example later on, maybe hopefully I can show it. You may have
why multiple hypotheses? Why do we have to use multiple hypotheses?
Because
Okay.
we don't know which one is perfect.
Let's look at this one. So this is your hypothesis set. P1 price P2. How many, P1, P2, okay? How many hypotheses do you have? You can choose P1 and P2, any value, right? So hypothesis set, you have infinite number eventually. You don't want to find the best rectangle, is the positives and negatives. So to do that, you need to explore infinite number of rectangles normally.
Sorry, can you tell me the goal in this rectangle?
So the thing is that you don't know what is out there in the real life, right? We don't know the exact hypothesis which is the perfect one.
Yeah.
So we need to explore some to find the perfect one.
But we're doing the sampling. We're talking about the sampling hypothesis.
This is the, let's go back here, look at this. So our goal is, these are positives, these are negatives. I want to find the best rectangle that fits or that has the positives inside, okay? So for that purpose, I have infinite number of
That's rectangle.
rectangles. So that's my M is infinite. So I don't have 2 or 3 or 4 or 5. I have infinite number of rectangles.
Rectangle that contains the plus.
No, I can draw infinite number of rectangles in this area, whether they contain pluses or not. So
And-
that's why I have infinite number of rectangles.
Yes, and we want to find a rectangle that is,
Our goal is, okay, this is the question that we are, that's a very, I really like your thought process. How do you come up with a rectangle that really works well with the positives? How do you know that you are not lucky with that rectangle? How do you know that rectangle will work in real life as well? Because the only thing you are given this, but you haven't seen the other data yet. There are unseen data. How do you know it's going to work in real life? Okay, that's what we are trying to solve. So you are not finding a solution by chance. Your solution is reliable. You can limit the error on your solution. So error is limited. That's the general goal of this, lecture.
so for example, we have this area with data.
Yes.
We're trying to find a rectangle that has the most positive or.
Yeah, you need to find the best rectangle that has the positives inside and negative. That's your goal. But the question that what we are covering is how do you know your rectangle is you are not lucky? I mean, how do you know it works? Because there are unseen data. So how do you know it's going to work for unseen data as well?
Best rectangle in this context mean the largest or the smallest, or the one that.
What's the,
We'll come to that. Which one is the best?
Oh, okay.
what's
So
the
we're working out a
properties
method.
of the. I think your question is like, how would you measure that this is the best?
Yeah, I think I'm lost into the specific of the problem, but I guess the problem, the problem of what type of, but I guess the problem here is how do we find a method that select the best rectangle without that concerning the whole population without.
Yeah, that's part of the problem. But the main problem we are looking into is you pick this rectangle as your hypothesis set. Based on your hypothesis set, why don't you pick circle? How do you know rectangle works better than circle? Maybe rectangle will make you lucky, but circle is a better choice for you. How do you know that rectangle will work better for you? But that's what we are looking at. So whatever hypothesis that you choose, you are not getting lucky. You are actually solving the problem. And lucky means you are not getting a good solution by chance. Of course, if you get a 20% accuracy, you know that your rectangle is not good enough. Okay. But whenever your rectangle is 99% accurate, can I rely on it? Can I use it in real life? That is something that we need to be sure when you develop train a model based on a small set of samples.
Rectangle means the method to find.
The method, yes. The rectangle is the method.
Okay. Oh, so now why?
So for example, method is K&N is one method that you know. So K&N is a hypothesis set, so that's one method. We are going to see Bayesian classifiers, that's another method. Region trees is another method. Neural networks, another method. Okay, so, or the one that I showed earlier, perceptrons with weight etc., that's another method. So each of these is a method. How do you know? You try multiple techniques. How do you know which one is more reliable in the real world?
That makes more sense now.
Okay, all right.
So
What's triangle? Yeah.
Yeah.
So now I'll go back to the hypothesis thing. Why is it related?
Which one?
Maybe why hypothesis then? Yeah, the infinite hypothesis.
Yeah. So if you have infinite number of hypotheses, okay, let me show you something like this. Okay, let me go back to this one. So if I pick, let me pick this one, it's fine. I can draw, if your hypothesis set is infinite, I can draw like this. Okay, I'm just drawing. Okay, just like this, just like this, just like this, okay, just like this, and I can draw exactly the positives, the area that I would want to keep positive inside. Okay, or if I make it positive 2 like this, okay, then I have negative like this, can make this like this, okay? Just draw like line and then like this, so I can do it. I don't need to draw a rectangle, okay? Which one is better for you? You want that small circles that connect to each other, or this one? The curly tab or the rectangle is better? Which one is better?
Curly?
Yeah, curly seems better, right? But the problem is, curly is fitting into training data. You fit your curves on the training data. It may not work well for the real data. It works for training, but it may fail because it's just customized for training data. You never know it's going to work bad for it. The rectangle will work better in real life.
So, so when you talk about the rectangle in this lecture, it means a method rather than a rectangle.
So when I say rectangle is a method, yes. For example, KNN is a type of method. Okay, it's a method. KNN is a method. But once you build the model at the end, that is going to be one rectangle.
Why is it characterized as a rectangle? What, like, why a model is a rectangle, I guess?
It's a model.
It's not as a rectangle, can be any shape.
Any shape.
It can be. any
It's just
shape.
an analogy.
Depends on your data.
It's an analogy here.
Obviously.
That can be of any shape,
Yeah.
but I limit my hypothesis set to rectangles. But what I'm saying is, let me show this slide. I was going to show it later. I have to put to see, okay? Now, let's see. So it's over time, but it may be good to cover this example. So I have different hypotheses or the models, they have power. Neural networks, deep learning, we learn that they can learn very powerfully, right? But for some learners, if you just do a line separated, they are not so powerful. Let's say that if I say draw a line that separates these two data based on training, probably the best line you can do, curve, including curves, not a straight line, will be something like this. You look at the training data. What is the accuracy now? 100%. Okay? But let's say that this is a very complex hypothesis. So this is a very complex hypothesis because it goes up and down, up and down, up and down. But let's say if you draw a simple hypothesis, a single line like this, what does it do? What's the accuracy? It makes some mistake, right? But it is still good enough, but makes some mistakes. Now, but this is based on the training data you have seen. It worked, the curve worked perfect. Now I'm going to add some unseen data because we haven't seen them yet. Okay, so these are the blue rectangles are the new data, and then yellow ones are the new unseen data. If you draw these curves again, you see curve made too many mistakes. But now the straight line works better in the real environment. Because your hypothesis was too powerful to fit on the training data. So you want to make sure that it doesn't happen. So we look at the power of your hypothesis set, and it is not fitting to the training set. So the error that you have, for example, the curve had a very low error on the training set, but very high error on the test data set. So this is not an acceptable case, okay? This is a problem. But for straight line, the error is similar actually. For the training and test, it's similar. It's a more reliable method.
So I guess the meaning of hypothesis is something like what the model assumed to be true in real world. That's the meaning of hypothesis.
Yes, that's what we are trying to solve, right? We build a model so that it should fit the training data, right? Training we have x1, y1, x2, y2. We try to find that function, right? That's what we go back into original slide. So the learning problem. So we need to find G basically. G is one from here. G belongs to here. We want to make sure that it assumes that V is similar to F, the real one.
So a function, so a hypothesis takes form of a function.
You can always like a function, yes.
Oh.
Because for each input data, you have an output, right?
Oh, that's it. Oh, okay.
For this data, you have a class label. All right. So thank you.